Thin airfoil theory is just one of our theories. It's just a way to predict the lift and the pitching moment on an airfoil. And this was developed 100 years ago. One of the challenges, see, it's built on potential flow. One of the challenges of thin airfoil theory is that it doesn't, drawbacks of the theory is that it doesn't predict any drag, right? Potential flow in general can't tell us drag on an airfoil. And so, so what we're doing here is we've got some theory that will help us at least predict the lift and the pitching moment on that comes from an airfoil. And why would we want to do that? So if we go back to day one, and we're looking at a full aircraft here, what we kind of decided is that one way to estimate the aerodynamics of this aircraft is to assume that the flow is basically is aligned with these wings pretty well. Okay, so that the cross section, if you take a cross section here of that wing, that's an airfoil, right? And so what we're trying to do is figure out, well, in general, what we want to know is what's the total force on this aircraft due to the aerodynamics, right? And those aerodynamics depend on, well, it depends on the angle of attack or the direction that velocity is hitting the aircraft. It depends on a whole bunch of things, actually. The Reynolds number, how quickly are we flying? So that would be Reynolds number, the velocity, the density, the viscosity in the air. It also depends on our flaps. So if we have, let's say we have a horizontal tailback here and it's got an elevator deflected, right? So it depends on that. It depends on maybe if we have our flaps here sticking out, then that's going to affect the force on this aircraft. And so basically we're just trying to figure out, how do we predict the force on some aircraft while it's flying through the air? And early on we decided, well, we're going to cut it up. We're going to neglect the fuselage for now and assume that the major forces are coming from the wings. And the way we can analyze at least the main wing or any of the individual wings really is to cut it up like this and look at the airfoil. What's the aerodynamics happening on the airfoil, right? So on this airfoil, we're going to have some total force on that airfoil, and also a pitching moment. We use a little m for that. So now the force and the pitching moment actually is just an integral of all of the pressure, right? If we looked around this whole airfoil and we knew what the pressure was at every point, and not only pressure, if we zoom in on the surface of that airfoil, we've got pressure that's acting normal to the surface. Then we also have some shear happening tangential to the surface. Well, it turns out that shear, we call this tau at the wall, is equal to mu du dy. We really haven't talked about this much, but what I wanted to show is that it depends on the viscosity. Well, at a first cut here, we're going to neglect viscosity. We're going to say that we're, for potential flow, we're neglecting the effects of viscosity, at least in this sense. And so we're only going to look at the pressure forces, okay? So the pressure is dominated by the inviscid flow, the potential flow. And so if we just knew the pressure all the way around this airfoil, we could sum that up and get an estimate for the forces. Now, unfortunately, by neglecting viscosity, we cannot get, we can't predict any drag. So the force that we're going to get on this airfoil is going to be, let me choose another color here, is going to be really mostly in this direction, in the lift direction, because it's not going to be able to predict any drag on the airfoil. So the lift is always perpendicular to the incoming velocities. So actually, if the incoming velocity here is relative to alpha, so that's v infinity, the lift is actually is acting perpendicular to that. And that's really the only force we're going to be able to predict once we sum up all these pressures, because we're neglecting viscosity here. Okay, so we can predict the lift, and then we can also predict the pitching moment. Now, the pitching moment depends on, this is a little different than a force. The force, we just integrate the pressures and their directions. We integrate that up, and we get a force, and we could actually draw that force acting anywhere along that airfoil. It's just a force. It's the integral of all that. It's almost like integrating the weight, right? The weight is acting in a certain direction, but it doesn't pertain to a certain location on the airfoil. It's just what the weight of that thing is, or the force that's being generated. But the pitching moment is a little different, because when we integrate these pressures, we can integrate them. My picture's getting a little messy here. Let me draw another airfoil over here, so we have some more space to work with. So when we integrate these pressures around the airfoil to evaluate a moment, we have to choose a location about which to compute that moment, right? So if we choose the leading edge, then we'll get the pitching moment about the leading edge. We could have just as easily chosen the trailing edge and computed the pitching moment about the trailing edge. The nice thing is, once we've integrated it about one point, we know exactly what the pitching moment is at every location, because we also know what the force is. So if I know the pitching moment at the leading edge, I can figure out what the pitching moment is at any other location by using the force and just moving. This is a statics problem, right? We just move over to another location, compute the pitching moment at that location. Well, it turns out that we really like the quarter chord, this location here, C/4, and that location falls out of thin airfoil theory, because thin airfoil theory predicts that that's the aerodynamic center of the airfoil. And so a lot of data, when you pull down data online for the lift and the pitching moment on an airfoil, the moments are usually summed about the quarter chord. Okay, that's just kind of standard convention, because that's really close to the aerodynamic center. Okay, so what we're trying to do here with this thin airfoil theory is we're trying to figure out, how we've got to be able to predict the lift and the pitching moment on this airfoil. And one way to do that is to neglect the thickness and just use the camber line of that airfoil. And so we're gonna say, when this velocity comes in, we're gonna force that flow to flow along the camber line. We're gonna force that camber line to become a streamline of the flow. And by doing that, we can integrate the pressure along the surface of that camber line and estimate what the lift and the pitching moment are, okay? So that's where thin airfoil theory comes from. Now, so let's step back to these equations here. And by the way, this is all on that Aeronautics Engineering Handbook, which is just kind of a summary of these equations. And obviously these are in the book as well. So let's go here to airfoil theory. So this is a section on airfoil theory where we're showing, like, these are the equations for how you define an airfoil geometry. And here is the equation for the camber line for a NACA 4-digit series airfoil. Okay, so this is a camber line that should look kind of familiar to you, because this is what 4.2 is all about. We're taking this NACA 4-digit series, which is a very common family of airfoils that was developed about 80 years ago in the 1940s. I believe is when they did, or 30s, 40s in that area. So anyway, they came up with this camber line, and of course this camber line has to start at 0 at the leading edge and then come back to 0 at the trailing edge. And so if we normalize it by the length of the airfoil, that's from 0 to 1. And so the digits, the 4 digits, tell us the location. So XMC is the location of maximum camber. I didn't draw this very well, but pretend like that's the location of maximum camber. And YMC is the value of the maximum camber at XMC, right? And that comes from these 4 digits. And then the last 2 digits. So for example, we're working on the 2412 airfoil. The 2 tells me that that's the YMC. So we're going to have 2%. So I could put a 0.02 here. 2% camber at XMC equals 0.4. That's what the 4 means, is that we're at 40% of the chord is a location of maximum camber, and we have 2% camber. And these are both in percent of the length of the airfoil, okay? And then the 12 back here, these last 2 digits, tell us how thick the airfoil is. And of course, with thin airfoil theory, we don't care, because thin airfoil theory just assumes that the airfoil is perfectly thin, okay? So we don't really care about that for our problem, okay? All right, so let's move on to thin airfoil theory here. So thin airfoil theory, and I developed this in the videos, it's in the books, and but basically this is the fundamental equation. You can use this requirement that we're going to force the flow to be a streamline of this camber line, and you come up with this fundamental equation where the strength of gamma, remember gamma as a function of x here, is the strength of the vorticity, the sheet of vorticity that we're going to put here along that airfoil, and that vorticity has to be related to the slope of the camber line, right? Which makes a lot of sense. I mean, I haven't re-derived it here, but it would make sense that the strength of that vorticity has to be related to the camber line, because if you have a really sharp camber line and you're trying to make that a streamline of the flow, that's going to change the strength of the vorticity along there, right, in order to make that be true. So this is the fundamental equation, and we're going to apply this cut a condition at the trailing edge that says that right here gamma has to be equal to 0. And what that does is it forces the flow to exit the trailing edge tangential to the trailing edge, okay? Well, this equation is kind of nasty to solve, this guy. That's our fundamental equation. And so the way that they solved it was by applying this change of variables to get out of x into theta. And then when you do that, and then assume that gamma is an infinite series, an infinite sine series, it's got this term up front, and then it is an infinite sine series, then you can prove, and I don't think I walked through this in the videos, you can look this up if you want to prove this yourself, but you can prove that that gamma will be a solution to this problem if these are the values of these coefficients. We have this A0 and then AJ terms in here. So if this is true, then gamma will satisfy this fundamental equation up here that we have at the top, okay? It will satisfy this equation here. So what we need to do is we just need to compute these A values, and if this is true, if A naught is computed is related to the slope of the camber line this way, then I can plug this into here, and that now becomes a solution to this equation up here. Well, you can take this one step further, and from the gamma, we can actually integrate gamma across the length of the airfoil and compute what the lift would be once we have a gamma distribution. So from this gamma distribution, you can integrate that and get the lift coefficient for that airfoil. And once you work through that integral here, you see that it actually only depends on A0 and A1. Now we have an A0 here, and then we have an AJ here, because this is an infinite series. So we've got as many A's as you want to carry out on this thing, right? We could compute as many as we wanted, but we only, in order to get the lift coefficient, we only have to compute the very first term. I mean, are we so lucky? Imagine if it required 50 terms, to compute the lift coefficient. We're pretty lucky that we only have to compute 2 of these coefficients here, or these constants, in order to compute the lift. So you can write that, you can compute these using these integrals here. You could also just plug in these integrals directly, because we've got an A naught plus an A1. These are both integrals from 0 to pi. Remember, the 0 to pi is now our limits of integration across that airfoil. So instead of going from x equals 0 to x equals c, we're going to go from theta equals 0 to theta equals pi. And that's what happened when we did this change of variables right here. We just changed it into theta instead. So that's why our limits of integration come out to be 0 to pi. And so because A naught and AJ, or whatever we want there, I'll go across the entire airfoil. We need that integral across the whole thing. You can combine this for A0 and A1 by plugging a 1 in here. And this is a typo, actually. I need to fix this. That should be a J right there. So I'll fix that in the write-up and re-upload it. So anyway, we can plug those two integrals in and actually combine them into a single integral if we wanted to, and plug it into this equation. So to compute the lift coefficient, we can either compute A0 and A1 from these integrals, or we can just compute this combined integral, which is the same thing. And when we do that, we'll find that we get something that looks just like this. We've got an alpha out front. We get a 2 pi out front. That just falls out here. We've got a 2 pi, and then we've got an alpha, and then we have some term here that depends only on the slope of the camber line. Okay, and then this integral from theta equals 0 to pi. And so this equation here is very common. This basically is our lift slope. So this is our change in lift with respect to alpha. And then we've got alpha here, and then a 0 lift angle of attack. Okay, so we can compute the 0 lift angle of attack all by itself from this integral there. So that should be pretty obvious. And that just depends on the slope of the camber line. Then we can also compute the pitching moment about the leading edge. So instead of just integrating, see, we integrated this over the whole length to get the lift. We can integrate it again over the entire thing and compute it relative to the leading edge to get this pitching moment. So this is the equation for the pitching moment. And it turns out you can compute that by, you just need to know the lift coefficient and then A2 and A1. So those A2 and A1 both come from this equation here. We're going to have an A2, A sub 2 is cosine of 2 theta, A sub 1 is cosine of 1 theta. So you can plug those in there, or you can combine the integrals just like before and write it this way. So it turns out that you can rewrite as the lift coefficient over 4, or the negative of that, added to the pitching moment about the quarter chord. It turns out that the pitching moment about the quarter chord just falls out of that equation, in fact. So anyway, and that's, you just compute that from that integral right there. Okay, and then once we know that, it's just there's a bunch of things we can do, but one of them is to compute the center of pressure, and so we can put that in terms of this thin airfoil theory as well. So that's just a computation of what point on the airfoil is could we integrate about to get 0 pitching moment. So anyway, that's just kind of an interesting thing that we can compute there. Okay, so what we're trying to do here is apply this theory to the NACA 4-digit series. All right, so let's go back over to 4.2. So we've got this camber line, and what we're trying to do here is, this is the definition of that camber line, and what we want to do is plug this into thin airfoil theory now to figure out what our lift and pitching moment are. And really, to get that, because the lift equation, remember CL equals 2 pi times alpha minus alpha L0. Those are alphas, sorry. Sometimes my alphas and 2 look really similar, so you gotta be careful. But every airfoil only differs in its 0 lift angle of attack, according to thin airfoil theory, because from thin airfoil theory, we're always going to get a 2 pi there, we're always going to get an alpha there. This is the only term that differs between every airfoil that's out there from thin airfoil theory. So once we compute alpha L0, we actually know exactly what the lift coefficient is at any angle of attack as predicted by thin airfoil theory. So that's what we're asked to find here. Use thin airfoil theory to predict the 0 lift angle of attack and the quarter chord pitching moment of the NACA 2412 airfoil. Okay, so here's our camber line, and you guys are all going to get a copy of this at the end of the day. This is the solution to this problem. Okay, so the first thing we need, we've got to figure out this dyc dx. That's all throughout these integrals, right? So we need the derivative of the camber line with respect to x, and so we can do that directly. We can just we can differentiate this with respect to x, and we'll get a bunch of stuff here. The way that we've worked through it, and this is thanks to Ben. Ben has put together this solution here for us, but the way that he liked to do it is to non-dimensionalize the camber line first and put it in terms of yc over c and x over c. So you can divide this whole thing through by c, just divide by c there, divide by c, and then all of these x's you can put over c, xmc's over c. Anyway, you can work through that and divide everything by c's, and then these c's here turn into ones, and so you get things in terms of like a 1 minus x over c, for example, right? And so now all of this is just in percent chord, all right? We didn't change anything inherently about this equation. We just put it in a slightly different form. And now he's going to take the derivative of dyc over c with dx over c. Same math. It doesn't matter which way you do it. You could have done it this way, or you could do it in non-dimensional form here. You'll get the same result either way. So so this is the derivative of that with respect to x over c. And now we've got to perform our change of variables here. This is our change of variables here to get it into theta. And this is just a little bit trippy here. We've got an equation. So if this is our camber line, we have one equation that takes us up to the point of maximum camber, and then we have another equation that takes us down out to the trailing edge. Okay, so so this goes from 0 to x over c of 1, and then in theta it goes from 0 to pi. Well, our integral is always from 0 to pi, right? We're always integrating across that entire thing. Well, now we have two equations, so we're going to have to integrate one of those out to this point here. So we've got to figure out what theta MC is, the location of maximum camber, and then we're going to use another integral to integrate the rest of the way. Okay, so we compute theta MC from the same change of variables from XMC. We know that location XMC, and we just plug it into the same change of variables to compute theta MC. So this is now the same equation here where we've changed our limits of integration from 0 to theta MC out to pi. And then we've swapped out inside of here, we've swapped out the x over c values. Remember these xmc over c's and ymc's, those are just constants. Those are just numbers, right? That's a 0.2 or a 0.04 or whatever it is, based off of this airfoil. So those don't need to be, our variables don't need to be changed for that. It's just the x over c stuff in here that we see is going to be swapped out with this change of variables. Okay. Okay, so now we have this equation, and here it's just simplified a little bit more, combined some terms. And now we've got to figure out these coefficients. Remember, in order to get alpha L0, we have to compute A0 and A1. Okay, so these are the equations for those coefficients. So here's A0. A0 is alpha minus 1 over pi, and then this integral. So we're going to divide up that integral. We've got alpha minus 1 over pi, and now we're going to divide up that integral from 0 to theta MC, and then from theta MC to pi. In the first one, we're going to plug in this first equation because that's our camber line up to that point. And then in the second equation, we're going to plug that in here. So that's the second part of that integral from theta MC up to pi. Okay. Now I'm not going to walk through the evaluation of the integrals. It's done here in painful detail. So hopefully you don't have any questions. But he's shown here exactly, all the processes for evaluating these integrals. And one thing that Ben did here, which you don't have to do, is he left this XMC over C and YMC over C as variables. They're just things that we're going to carry around in this integration. The benefit of that is that at the end of this, we have a solution that we can plug in any NACA 4-digit series equation to, because he left those as variables. Now, I think in a lot of your groups, you've actually plugged in values for that, and that's just fine to solve this problem. These, again, are just numbers, right, that we know based off of the 2412 airfoil. So you could have just plugged those in directly. He leaves those as variables as he works through this integration. So he gets here to A0, and then Now he's ready to plug in these variables from the 2412, and also theta MC he left as a variable there. So once you plug in those values, then this now all simplifies down to A naught equals pi minus this 0.0449, okay? And he was kind enough to also check this with Wolfram alpha, so you can plug this integral in numerically, and so there will be a link there that you can click on and see that this is the same number that Wolfram alpha comes out with for that integral. Okay, so on to A1, that's the other one that we need to do. So here's the integral again. We're splitting that up from 0 to theta MC to pi, and we work through that integral. Again, you've got all the detail there, so hopefully you can find any mistakes that you might be making. Plug in these numbers, and we get this value for A1, okay? So next, he computes A2. Now we're gonna need A2 for the pitching moment. For the zero lift angle of attack, we really only need A0 and A1, but might as well go ahead and do A2 at the same time. So this is the integral for A2. Again, the exact same thing. Each of these integrals is just a little bit different. So here we've got a cosine 2 theta that we're multiplying by dy dc. Before we had a cosine theta multiplied by this dy dc. And in the original integral, we didn't have anything that we were multiplying by it. So if you look at these equations, the first one is just the integral of the camber line itself, or the slope of the camber line. And then any of these other integrals are just the slope of the camber line multiplied by cosine of n times theta. So A1 is cosine of 1 theta, A2 is cosine of 2 theta, right? So anyway, so each time we do this integral, we're just kind of incrementing on this cosine term here. So we do A2, and this is the solution that you get for A2. And now we can just plug these in. So the lift coefficient is equal to A naught plus 1/2 A1. We can write it in this form where alpha L0 is A naught minus A1 there. And so you can compute alpha L0, and you get minus 2.1 degrees here. And by the way, the numbers that actually come out of this are in radians, okay? So you gotta remember, whenever we're dealing with angles of attack, the numerics, we're dealing in radians, but a lot of times we wanna switch that to degrees when we actually print that out, because not many of us can visualize what 0.03 radians really means, you know, but we can visualize what 2 degrees is. So we've got a minus 2 degrees, and then we plug in these values A2 and A1 to get the pitching moment at the quarter chord, and we get minus 0.053, okay? All right, so let's see what that means now. So what we have here, if we were to plot the lift as a function of angle of attack, what would we expect this to look like? Well, thin airfoil theory actually predicts that every single lift as a function of angle of attack looks identical. They all have the exact same slope here, a linear relationship of 2 pi between the lift coefficient and angle of attack, right? So CL equals 2 pi times alpha minus alpha L0. That's the equation that comes out of thin airfoil theory. So anyway, every one of these airfoils that we ever plot from thin airfoil theory is going to have a lift relationship with angle of attack that looks like this. So what does that mean? Well, that means that on this airfoil, if I increase the angle of attack, so here's V infinity here, my lift, and I'm just going to draw it at the quarter chord. Again, we could draw that anywhere, but my lift that's perpendicular here is going to grow linearly with the angle of attack. If I go from let's say, from like 0 degrees angle of attack up to 1 degree angle of attack, I'm going to have a linear change in my lift. My lift is going to increase by actually exactly 2 pi, right? Multiplied by my the 1 degree. I'd have to change that to radians, because again, this is in radians. So 2 pi times radians. So that's how much my lift is going to grow. If I increase angle of attack, my lift is going to go up. If I decrease my angle of attack, it's going to go down, right? So that comes right out of thin airfoil theory. So now what we computed here was the 0 lift angle of attack. That is the point where this lift curve crosses zero. It's the angle of attack that would produce zero lift on this airfoil. And we see that that's at -2 degrees. So we could, we put a point here. So this is alpha L0 at -2 degrees. That's where this line crosses the axis. And so if we were flying at -2 degrees, and we can visualize that here, if our angle of attack was negative here. So if our V infinity was coming in from the top of the airfoil, but at a -2 degrees, that would produce zero lift on this airfoil. Okay, so that's what we get out of that. And then the pitching moment at the quarter chord is this number here. Now, pitching moment in general, if we were to look at the pitching moment at the leading edge, for example, we would find that it looks something like this. So this is the pitching moment. Here's a Cm as a function of alpha. And if we were to look at the pitching moment at the leading edge, we'd actually see that there's a linear relationship between pitching moment and angle of attack. But there's something special about the quarter chord. The pitching moment at the quarter chord is actually independent of angle of attack. We get a constant. We get a constant. This is the pitching moment about the quarter chord, and it doesn't change with angle of attack. Why is that? Why doesn't the pitching moment change about the quarter chord with angle of attack? Okay, Trevor, you got it exactly. It's because it is the aerodynamic center as predicted by thin airfoil theory. So thin airfoil theory says that there's a special location at the quarter chord here where the change in pitching moment, so change in pitching moment with respect to alpha is zero, okay? That's the definition of the aerodynamic center. Now we're gonna define that for not only an airfoil, but for an entire airplane. And so we'll talk about that. You know, this definition holds more broadly than just from thin airfoil theory. This is just a definition for the location of the aerodynamic center. It's this special place on this object where the pitching moment doesn't change if we change angle of attack. Okay, but thin airfoil theory says that happens exactly at the quarter chord. And so if you compute the pitching moment about the quarter chord, that is going to be independent of angle of attack. And that's what we see here. That's what this number is right there. Okay.